Suppose we have an elliptic cylinder, x squared over a squared plus y squared over b squared is equal to 1. Okay, x squared over a squared plus y squared over b squared is equal to 1. Here we can conclude that a and b are both non-zero, otherwise you're dividing by 0, which is bad. So how this is going to look on the xy plane is something like this. So this would be minus a, or here I'm also assuming a and b are both positive, but if a was negative, then negative a would be positive. So here's what we have. Okay, this is just a general case. So it's an ellipse, okay, an oval, but on the so this is just on the xy plane, but then on the entire R3, or in 3D, where you have a z component, it will look like this. So you still have that oval, okay, but it's a elliptic cylinder, so just keep on going up and down, where each of the horizontal cross section is this oval. Okay, so this will be a minus a, b minus b. Okay, so and this just keeps on going up, and this keeps on going down. Okay, so the question is, I want to find the equation of a plane that passes through the origin such that the intersection between the plane and this elliptic cylinder is going to be a circle. Okay, so then if I have a plane, okay, and I intersect it, okay, at this, intersect it with this elliptic cylinder, somehow this intersection, it's going to be a circle. Probably going to be tilted. Of course, the circle is not parallel to the xy plane, but nonetheless, the intersection is going to be a circle. So this is a bit of a head scratcher. So first of all, what we want to do is we want to find the equation of this plane, okay, that passes through the origin. So normally a plane is ax plus by plus cz is equal to d. But in this case, because it passes through the origin, okay, this d is going to be 0. Okay, if you let x, y, and z, because x, y, and z is a solution, it's on this plane. Okay, so the point is 0, 0, 0, so x, y, and z are all zeros. So then you get 0 plus 0 plus 0 is equal to 0. So the constant is 0. Okay, so now I want to rearrange for z. I get z is equal to, actually I'm going to call these primes for now, because I'll use capital A and capital B later. It doesn't matter what you call them, because they're just variables for constants, letters for constants, okay? So then z is going to equal to minus a prime x minus b prime y, but we're dividing by c prime over here, so divide by c prime, and I should divide by c prime here. And I'll call this new negative a prime over c prime, I'll call that capital A, so I have capital AX, and then plus, I'll call this negative b prime over c prime capital B. Okay, so we have that. Here we just need to, and then we can just use this. Like, we just need to find a and b. We don't care about the a primes and b primes. One thing to note is that c prime can't equal to 0, which from here does make sense, not only because it's in the denominator, okay, so you can't divide by 0, but it's like, if you let c prime equal to 0, then all you're left with is this kind of plane, so ax plus a prime x plus b prime y is equal to 0, and what that's going to look like on the xy plane is a line that passed through the origin, and maybe it looks like that. But this would cut this elliptic cylinder. So this isn't from an aerial point of view. It will cut the elliptic cylinders straight up and down. So there is no way for the intersection to be a circle, okay? Because the intersection is just going to be essentially just two lines just going up and down forever, okay? So because the plane's normal vector is perpendicular to I guess the xy plane, okay? So then you're not going to get intersection anywhere else. Okay, so this is just a visual reason why that C prime also cannot equal to 0. Okay, because we need to make sure that the intersection isn't just at these 2 points. So in a 3D version, it's going to go straight up and down. You're just cutting the cylinder straight up and down. You're not going to cut across it or slice through it. Okay, so this is what we have. Now, let's parameterize our elliptic cylinder now. So we have x divided by a whole thing squared plus y divided by b whole thing squared is equal to 1. So generally, how do we parameterize something like this? Well, we can let the first part equal to cosine of t, and we can let the second part y over b equal to sine of t. Okay, and this will imply that x is equal to a cosine of t and y is equal to b sine of t. I could add that t is going to be between 0 and 2 pi, but we won't need it for this question. Okay, so now what does this mean? This means that z is going to be a times x, which is little a cosine of t, plus capital B y. So capital B times little b sine of t. Now I don't want to say a and b all the time, so actually I'm going to change capital A here to little m, capital B here to little n. So this way I won't be saying big A, little a, right? Big B, little b, so like that. Okay, so then we have our parameterization, right, of the intersection of the plane and the what do you call it, the elliptic cylinder. So we have r of t is going to equal to x of t, y of t, z of t, which equals to a cosine of t, b sine of t, and then z of t is just all of this, so copy and paste. Okay, so now what we see here is that we need to make sure that this is going to parameterize a circle, okay, tilted circle. So what I'm going to do here is I'm going to find some position vector. So I'll start with r of 0. So r of 0, when the angle is 0, right, you're going to be somewhere, so when the angle is 0, okay, you're going to, the radius is going to be pointing towards the positive x-axis. Okay, so when your radius is 0, your y coordinate should be 0, which is what we have over here. A for the x value, and then the z value is going to be ma. Okay, and then r of pi over 2 is going to be equal to, so at 90 degrees or pi over 2 radians, your radius is pointing along the y-axis, okay? Which means that you're somewhere, so this point initially for the r of 0, this point is going to be somewhere on the xz plane, and then r of pi over 2 is going to be a point somewhere on the yz plane. Okay, so we get x to be 0 here, we get y to be b, and then z is going to be nb. Okay, so then this is what we have. Now why do we do that? Visually speaking, let me just do this over here. So maybe r of 0 could be, so we're at 0 degrees, right? Or 0 radians, but maybe it's somewhere a bit lower, right? And then r of pi over 2, we're at 90 degrees, or pi over 2 radians, but we're probably somewhere higher. Okay, like that. So it looks like that. Okay, and these are perpendicular to each other. Okay, so that's what we have. Okay, so then speaking of the fact that they're perpendicular to each other, we have two conditions. Okay, so the first condition is that these two position vectors are perpendicular to each other, orthogonal to each other. Okay, what does this mean? It means that their dot product is equal to 0. So what is their dot product though? Their dot product is a times 0 is 0, 0 times b is 0, and then ma times n times nb, right? And we set that equal to 0 because of this orthogonality property, this condition. So then what does this imply? This implies that m is equal to 0 or n is equal to 0, because we already established the fact earlier that a and b cannot equal to 0. Okay, so a and b are non-zero, which means in order for this product to equal 0, m is equal to 0 or n is equal to 0. Okay, so now the second condition is that, well, since you're on a circle, right, probably a tilted circle, so these position vectors are going to be on the circle. They kind of like form, they're like the radius of the circle. Okay, so because let's say the circle is like tilted, let's say in this diagram, this position vector is going to be a bit lower on that's going to be below the xy plane, and this position vector, so this is going to be below, and then the other one is probably going to be above it, right? Well, just for the sake of this diagram, okay? So above the y plane, okay? So, but because these two vectors essentially form they're like the radius of the circle, okay? What does that mean? It means that their magnitudes are the same, right? So the magnitude, how do you find the magnitude of first one? It's just a squared plus 0 squared plus m squared a squared, right? And then you take the square root. But because the magnitudes are equal, the square of their magnitudes are also equal. So essentially I'm not gonna bother writing out the square root, okay? So they're both going to have the same magnitude, which means the square of their magnitude is the same. Like, this is true, right? So if this is true, then, you know, square both sides, then the square root goes away. Okay, so these are my two conditions, okay, that needs to be true. Now, with this in mind, I'm going to isolate for the variable. So if for example, if I want to isolate for m squared is equal to b squared plus n squared b squared minus a squared all over a squared, and n squared is just equal to a squared plus m squared a squared minus b squared all over b squared. Okay, so then why did I do that? Now, with these two conditions in mind, we have two cases. Well, actually, we have three cases, but specifically two cases, and the second case would have two subcases. Okay, so in total, you have like one and then two subcases. One case and then two subcases, so that's three cases. Okay, so I'll just break it up like this. So case one. What if A was equal to B? And then you probably guessed that the other cases A is not equal to B. But let's suppose A is equal to B. So if A was equal to B, what does this imply? So this implies that, well, actually, instead of saying A is equal to B, I'll say A squared is equal to B squared. Because over here, A and B might be negatives of each other. Like for this case, like if A squared is equal to B squared, this doesn't necessarily mean A is equal to B. Like A could equal negative B. But we just care about the fact that their square is equal to each other or not equal to each other. So let's take the case that they are equal to each other. So if A squared is equal to B squared, this implies that, okay, so what's the relationship between m squared and n squared if A squared and B squared equal to each other? So m squared is going to equal to, well, B squared is equal to A squared, right? So we just have A squared plus n squared A squared minus A squared over A squared. We see that A squared and negative A squared cancel, right? A squared minus A squared is 0, and then A squared over A squared is 1. So we get that m squared is equal to n squared. But what does this mean? This means that, notice that we need to have it where these two conditions must hold. So two conditions must hold in order for this parameterization to parameterize a circle, a tilted circle, maybe a tilted circle. And I say maybe because of this case. So in general, like if like it looks like a circle, right? So A squared is equal to B squared implies m squared is equal to n squared. But look, we have it that this condition must hold. N is equal to 0 or n is equal to 0 because of this orthogonality condition, right? Their dot product needs to equal 0. So we have it where one of m or n is 0, but m squared is equal to n squared. So, right? So if m is 0, well, either way, you're going to get 0. If m is 0, n is 0, and if n is 0, m is 0. So you have it where m is equal to n is equal to 0. So m is equal to 0 and n is equal to 0. So I should probably say by this condition right over here. Okay. So that's pretty cool. But what does this mean? This means, what does this say about our plane? Z is equal to mx plus ny. That's how we set up our plane to begin with, right? If m and n are both 0, then z is just equal to 0. Now, why is that the case? Well, if a squared is equal to b squared, then all you have is you have x squared over a squared plus y squared over a squared equals to 1, which implies that x squared plus y squared is equal to a squared. So in this case, our elliptic cylinder is just a circular cylinder, right? It's a nice cylinder where the cross-section is already a circle. Right? It's a circle with radius a. So therefore, if you have a plane that passes through the origin, that cuts through this cylinder, and the trace needs to be a circle, well, you can just let z equal to 0. Or the z equals 0 is just the xy plane, right? It's going to be a circle, okay? Like that. Because this is already x squared plus y squared is equal to a squared. Right? The cross-section, the horizontal cross-section of this cylinder is already a nice circle. So that's why z is equal to 0. So that makes sense. That's very cool. Okay. So that's for this case. So if a squared is equal to b squared, then the plane is just z is equal to 0. It's just the xy plane. But what about case 2, where a squared is not equal to b squared? Okay, and the two subcases will be if a squared is less than b squared or if a squared is larger than b squared. But for now, let's just focus on the general case that a squared is not equal to b squared. And then we'll tackle the two separate cases when one is bigger than the other later. And before I move on to case 2, now, I would just write it down, okay? So case 2 is when a squared is not equal to b squared. This implies what? So to do this problem, I will have to prove something else. Okay, so notice right over here, I stated that, so I stated from this, essentially this line, that a squared plus, if a squared was equal to b squared, right, this implies that m and n are both equal to 0, okay? But now what I want to do is I want to prove the converse. So I want to show that if m and n are both equal to 0, then a squared is equal to b squared. And we'll see why we do that later, why I did that, okay? So let's prove the converse. So the converse is the backwards direction. So just because this statement is true doesn't mean the converse is true, okay? If you have rain, then you will have clouds, but just because you have clouds doesn't mean you have rain, okay? So it could be a nice sunny day and there is no rain, but there could be nice clouds, blue skies, birds chirping, okay? So let's prove the converse. So then there's a little lemma right over here. It's like a subproof. So let's show that if m is equal to n is equal to 0, if they're both equal to 0, then a squared is equal to b squared. Okay, so if m is equal to n is equal to 0, this implies that, I'll just take this formula. This implies that 0 is going to equal to b squared and then plus, well, n is 0, right? So n squared is 0, okay? 0 times b squared is 0, and then minus a squared divided by a squared. What does this imply? This implies that, well, if you multiply a squared on both sides, 0 is equal to b squared minus a squared, and this implies add a squared on both sides, a squared is equal to b squared. Okay, so that will complete the converse. So what does this mean? It means that this is actually both directions. So I'm actually gonna I'm gonna erase all of this. Actually, I'll keep it. But essentially, from here we can conclude that from the forward direction and this backwards direction, that I'll call this lemma 1. Then lemma 2 is, well, this is an easy proof. Lemma 2 is, I get that a squared is equal to b squared implies m equal to n equal to 0, okay? And I have it where m is equal to n is equal to 0, which implies a squared is equal to b squared by lemma 1. So this first part is by this part, okay, and then the second part is by the lemma 1. This is actually the same thing as saying, so logically equivalent, okay, as another way to say that a squared is equal to b squared if and only if that m and n is both equal to 0. So actually I'll write that down. M is equal to 0, and I'll write out more. So and n is equal to 0. Okay. So what does this mean? It means that if if a squared is not equal to b squared, this is false, right? It is not the case that both m and n are equal to 0. So this would imply, what does this mean? That either m is non-zero or n is non-zero. Okay, so that's it. I just proved the converse of this direction so that I get this biconditional. So once you hold, if the converse is true, then the inverse is also true. So notice that this is the inverse to this statement over here. Okay, yeah, so proving the converse will prove the inverse to be true. Yeah, okay, so because you have that biconditional, right? So when the biconditional is true, the regular forward direction is true, and as a result the contrapositive is true, but then also the converse is true, and the contrapositive of the converse is the inverse, so the inverse is true. All of this is true, so it's a really powerful statement. Okay, essentially the two sides will always have the same truth values. Okay, either true for both or false. So if one side is false, the other side must be false. And if one side is true, the other side must be true. I'll go on a tangent because I believe that the biconditional is my most favorite logical operator, because when it comes to spouses, it's an if and only if. You have biconditional, it's two ways. It's a strong thing holding their relationship together. But anyways, back to math. But the thing is, though, one of them is true, right? Okay, you could have it where, so if you just have this alone, you could have it where m and n are both non-zero, okay? However, let's just take a look at them separately. If m is not equal to 0, combining it with, again, this orthogonality condition that we concluded that one of them must be 0. So if m is not equal to 0, what does that mean? It means that n has to be 0. Okay, because here I get that at least one of them is non-zero, but then here I get that at least one of them is 0. So in the case that m is not equal to 0, n has to be the one that is 0. And if n is the one not equal to 0, then okay, I'll do this. Then m is the one that is 0. Okay, so we get that. We have one non-zero number and then one 0 number. Okay, so let's take the case where m is non-zero and n is 0. So I'll probably do this again. Probably just highlight this part is sufficient. So if m is non-zero and n is 0, okay, then what does this mean? This implies that m squared is equal to b squared minus a squared divided by a squared, okay? And if n is non-zero and m is 0, then we get n, using this formula now, n squared is equal to a squared minus b squared over b squared, which implies that m is equal to, so when you take square root on both sides, don't forget the plus or minus, square root of b squared minus a squared, oh, there should be a squared over here, divided by a. Technically, there should be a plus or minus right here as well, but we don't need that because you're only going to get two cases, right? Positive divided by positive is positive, negative divided by negative is positive, positive divided by negative is negative, negative divided by positive is negative. Okay, so either way you get like the two negative cases, two positive cases. So it's just going to be plus or minus. Okay, positive case and a negative case. Okay, and n is equal to plus or minus square root of a squared minus b squared divided by b, which implies that z is equal to, so mx, right? So plus or minus square root of b squared minus a squared over a x. And this is when b squared is greater than a squared. So this is like the subcase I'm talking to you about. Because if b squared is smaller than a squared, this is negative. You cannot take square root of negative. And then you have z is equal to ny. So n is plus or minus square root of a squared minus b squared divided by b, y. Right? Because here m is 0, and then over here n is 0. Okay. And this is the case when a squared has to be larger than b squared. Or else, if it's not larger, if it's smaller, then this is going to be negative. Right? And if it's equal, then you're just going to get 0, right? So if you have a squared is equal to b squared, notice that you're just going to get z is equal to 0 for both, which we have already done over here. Okay? So you have your answers. Z is equal to 0. Z is equal to plus or minus square root b squared minus a squared over a, and z is equal to plus or minus square root of a squared over b squared over b. Wow. So those are the cases, okay? When a is equal to b, a squared is equal to b squared, when b squared is greater than a squared, and when a squared is bigger than b squared. So hope this was interesting to see. It's not a friendly problem at all.